All right, everybody, welcome back to Learning Calculus. And today's topic is perhaps one of the biggest. It's all about derivatives and differentiability. For a quick introduction and why I'm qualified to teach you some calculus, I think that math is fascinating. I just recently graduated and I earned a 5 on the AP Calculus BC exam, which is equivalent to Calculus 1 and Calculus 2. And when I grow up, I plan to teach calculus or some sort of math as a teacher. And remember, the best way to improve at calculus is by doing calculus work. So let's go over a quick agenda for today. We're going to talk about the derivative. If you've seen my previous episodes, it'll look familiar, but just in case if you haven't, we're going to talk everything you need to know about the derivative. And we're going to talk about rates of change and growth. And then we're going to talk about taking derivatives. So everything you need to know here: power rule, constant rules, trig functions, inverse trigs, exponent and log derivatives, and product and quotient rule, and then the chain rule. And then we're going to end with 2 applications of derivatives, which is implicit differentiation and L'Hopital's rule for indeterminate limits. Once again, this is not going to be my only video about derivatives. I've mentioned it before in this series. I'm going to have a couple talking about the actual applications of derivatives. This is everything you need to know functionality-wise of derivatives. All right, so if you've seen my previous episodes, this will look familiar. Can change occur in an instant? We're going to quickly go over this again and why, yes, change can occur in an instant. So once again, to recap, slope describes the rate of change between 2 different points. It's given by this equation right here. It's literally just a ratio of the difference in y divided by the difference in x. It's rise over run, how fast things change. So on the graph like this, which is just a linear line, it's really easy to tell what the slope is because you can see that the rate of change is 2. Every time you go 1 x unit over, you go up 2. However, if you want to use slope on something more confusing like a parabola, it's going to make the average rate of change. So this line is on average how things will change as you go across the parabola. But as you can see, the rate of change on the parabola goes down a little bit first, and then it goes up. So the slope that you make from the line will form a secant line. And as we've gone over, what we can do is we can turn that secant line into a tangent line, which describes instantaneous change. So we're going to rename our points. Instead of this first point being x f of x, it's just going to become, well, it's actually going to stay x f of x. This second point, instead of being f of x2, x2, we're going to rename it to have an h inside of it, where h is just an arbitrary number offsetting the points from each other. So our slope equation becomes f of x plus h minus f of x divided by x plus h minus x. And then as we've gone over, we can use a limit and have that limit approach 0. For h. So h will approach 0. That means that the distance these 2 points are offset will also approach 0, which makes the secant line transform into a tangent line. And we can see this in this GIF right here. The distance between the 2 points will approach 0, and when it becomes 0, the 2 points will be on top of each other, forming a tangent line. So once again, yes, change can occur in an instant, and that is called the derivative. The derivative describes slope in an instant. And these are the 2 common types of definitions you'll see. So this top one is just the derivative of f of x. Let's go over some notation. It can be written as f prime of x, which means the derivative of a function f of x. It can be written as d over dx, which means the derivative of something with respect to x. This is also an operator, so kind of like how you say plus to indicate that you add 2 numbers, or minus to subtract 2 numbers. D over dx is an operator. So when you see d over dx, that means you take the derivative of it. And then dy over dx is a little different. It means the derivative of a function y with respect to x. We'll go over a little bit more when we go over implicit differentiation, but this is really important. The bottom right here is just the derivative of a point, so f prime of a. And generally, you won't need to be able to solve derivatives with the limit definition, although it is super good to practice algebra, and recognizing what a derivative looks like is important. So if you see something where a limit is approaching a certain point or limit is approaching 0, and you see some functions, that probably means you're looking at a derivative. Okay, so let's go over a quick little definition use. So we have a function f of x equals x squared, and the question is written really sloppily by me with my mouse. What is f prime of x? So we're just going to find the function of the derivative. Let's use our limit definition, which is written right here and up in the corner, and let's plug x squared into this. So we have the limit as h approaches 0 of x squared. Oh wait, sorry, this is right up here. So x plus h squared minus x squared divided by h. And what we're going to do is we're eventually going to plan to plug the limit into the equation. So we're going to eventually solve it directly. But as you can see right now, if I were to plug h equals 0 into the equation, you're going to have a divide by 0 error. And that's common for most in fact, all derivatives. You have to algebraically manipulate it before you can solve it directly by plugging h equals 0 in. So you can FOIL out these two things. If you know the equation, it's right here, but I prefer just to write it out and be safe. You end up with x squared plus 2xh plus h squared, and then you have minus x squared, and it's still being divided by h, and you have your limit. As a quick aside, writing your limit is really important. I'm sure lots of teachers and lots of professors, I know that on the AP exams, writing your limit is really important because, you know, you're writing an incomplete problem. So make sure you keep your limit. It's really annoying to write every single time, but it's okay. You'll get used to it. In this step, you can see two things happen. So you have an x squared and a minus x squared, so those will cancel out. And then we're going to factor out an h from the remaining stuff. So we'll have 2xh plus h squared. Let's factor out an h. And that's what we're left with down here. So h times x squared plus h divided by h. And from here, it's pretty simple. We can cancel out the h's, and we're left with 2x plus h. When you plug the limit as h approaches 0, you see that the derivative of x squared is 2x. And let's talk about that a little more. And you'll see why in a second when you go over power rule. But let's talk about just the general relationship between derivatives and between normal functions. So here on Desmos, I have loaded up f of x equals x squared. And then I have f prime of x, which, as we just went over, is 2x. It's really cool just to look at this graph, understanding that when you're looking at a derivative, that means you are talking about the slope of the equation, which is super important. I personally was mixed up for a little while. I know that some of my friends were. It's confusing sometimes to realize that you're looking at a derivative, the slope. So let's talk about some moments. So when the slope is going down, you are decreasing in values with x squared. You can see, obviously, that the function will have a negative value. So a negative value indicates that you are moving downwards in the original equation. And as this slope becomes more gradual and it becomes closer to 0, obviously the derivative follows suit. You will cross through 0 at this point. And then once you start becoming positive again and your slope increases more and more and more and more, your derivative will also increase in value. And also just thinking about why x squared's derivative is 2x is really cool. It means that x squared changes at a rate that doubles itself, because that's what x squared is. X squared is just x times x. So the rate at which that grows will double itself over time. So it's really cool just to think about derivatives. And once again, when the function reaches the local minimum, so when x squared goes to its lowest point at 0, the value of the slope is also 0, because when you're at a local minimum, and we'll go over this in the next episode a lot deeper. But when you have a local minimum, that means that your equation has to stop. And at some point, the slope will be 0. So that's another really important thing that derivatives can tell you. It can tell you when local maximums and local minimums are in an equation. Okay, let's talk about differentiability and continuity. So in my previous episode, you'll remember we talked about continuity. If the limit from the right matches the limit of the left and the point itself matches, you have a continuous function. So that means that the function basically can be drawn without lifting your pencil. For a function to be differentiable, this is important. The function must be continuous. And also, you can say the one-sided derivatives must be equal. So the derivative leading into the point and the derivative leading out of the point must be equal. And here's really important. Differentiability implies continuity. If something is differentiable, that does mean it is continuous. It has to be. But continuity does not imply differentiability. Let's look at this. Here's the equation for the absolute value of x. And you can see most of it is differentiable. You can differentiate all the way up to here. It's -1, -1, -1, and then you get to 0. And something weird happens. It just instantly becomes positive. And the derivative starts becoming +1. And it goes on like that forever. Because you fail this condition right here, that the limit of the left derivative and the right derivative do not match, you can't differentiate absolute value of x at the point where at the vertex point. You can't differentiate that. And this is the same reason right here. You can't differentiate when it comes to a point. Because once again, you fail this condition. But also right here, this is 1 over x, the equation 1 over x, and this is not differentiable at the point 0 because you are discontinuous. So, you shoot off to infinity down here up from the negative direction, and then in the positive direction, you shoot up to positive infinity. As a quick aside, for something to be differentiable, it also cannot be a straight line, because at that point, think of the x cubed graph. I really wish I had a picture of it. X cubed kind of does this. It goes up really gradually in the negative direction, and then when it gets to 0, it goes up like this, straight up, and then it starts gradually decreasing in its slope as you go out from 0. At 0, you cannot differentiate x cubed, the cube root of x, because at 0, the cube root of x is increasing infinitely in value. The derivative would be infinity, but as I've been over, infinity is a concept, so that means that the derivative does not exist if your function goes straight up. So that's a quick little aside. I really wish I had a picture demonstrating that. I guess this picture kind of demonstrates it, because as you approach the point, so this is just square root of x and then negative square root of x. As you go closer into this point, the derivative becomes more and more steep, and at 0, your derivative will be pointing straight down, so it'll be negative infinity. So that means the equation will be decreasing at a rate of infinity. So that also makes this little equation right here, you call it a cusp, that makes it impossible to differentiate at 0. Okay, so let's talk about quickly some examples of rate of change, because as I've talked about, derivative just means rate of change. Let's take a look at a real-world example between position and velocity. So logically, position can be written as a function of time. It's normally written as s of t. And if position can be graphed as a function of time, that means that it's changing. The position's rate of change is something's velocity, which is normally indicated with v of t. Because if you think about it, when position is changing, what that means is it changes at different rates. So because velocity is the instant rate of change of an object's position, properties such as whether v of t is positive or negative or if it's zero can tell us how position is changing. So here's a quick little example. So when velocity or s prime of t is positive, that means that the rate of change of something's position will be increasing. So that means typically that the object is traveling vertically up or horizontally to the right. And inversely, if s prime of t or velocity is negative, that means the rate of change of something's position is decreasing. So it is traveling to the left, or that means that the object has traveled down. And then if v of t is zero, that means that the object has no movement and it is completely stopped. And even more so, the rate of change of velocity is acceleration, because acceleration describes how quickly an object speeds up or slows down. It's the rate of a rate, aka the second derivative, which is said right here in orange. And this down here is just a quick little demonstration of how these rates of change associate with each other. So s of t can turn into v of t, which is also the same as s prime of t. And that can turn into a of t, acceleration as a function of time, which is the same as s double prime or v prime of t. So rates of change are really important in calculus. We'll go over much more rates of change, but for right now, here's just a cool real world example of rates of change. Okay, let's talk about taking derivatives. Here we go. So luckily, you don't need to take the limit definition to take a derivative. Most of the time, unless you're explicitly told, you can use shortcuts in many different rules. So we're going to quickly just go over every single derivative rule. And as a quick little mention, all of these can be proved with the limit definition. So if you're not believing something, go look it up. The limit definition will show that all of these are true. So here's constant functions, and I pulled up a little Desmos picture of it. When you say that a function is just a constant, that means it's just a straight line. And because constants don't change, that's why it's constant. A constant's derivative is always zero. So whether that constant is 10 billion, whether that constant is 0.1, whether that constant is 5, that derivative will always be zero, because there's no change occurring at a constant. Here's the big one, power rule. Everyone loves the power rule. So do you remember how the derivative of x squared was 2x? So here it is. If a function f of x equals x to the power of n, where n is a rational number, f prime of x, so the derivative, is equal to n times x to the power of n minus 1. So you can think of it as dropping the power down in front of the x and then subtracting 1 from the power. So here's a quick couple of examples. So x to the power of 8. When you take the derivative, all you do is drop the 8 down in front and then you subtract 1 from the power. Here's one right here. F of x is equal to 2 times x to the power of 7. You just multiply those two numbers out in front because 2 is just being multiplied anyways. So when you drop down the 7, it becomes 2 times 7 times x to the power of 6, which is 14. And here's another example that's really useful when integrating. You'll get lots of fractions. 1 over x to the power of 3, if you remember your exponent rules, can be written as x to the negative third. And then using the power rule can show us that f prime of x is equal to negative 3 to the power of negative 3 times x to the power of negative 4, which once again, using the same exponent rule, you can rewrite as negative 3 divided by x to the power of positive 4. So power rule is a really big important one. Constant functions really easy. Let's talk more. Sum and difference rule. This one is really easy. So imagine that u and v are both differentiable functions. If you take the derivative of both of them being added or subtracted together, the answer is literally just u prime plus or minus v prime. Very easy. Sum and difference rule is easy. And that's why taking the derivative of polynomials is so easy, because you just use the power rule and the sum and difference rule. Let's talk about trigonometry derivatives. So this is where things become more interesting. Look at the red function, which is just sine of x. You can see that when sine of x is at 0, so that happens at 0. There's pi, it happens at 2 pi. Its rate of change is the fastest, because as you go up, your rate of change is increasing, and then as you pass through 0, your rate of change will start decreasing as you go up to 1. When you think about cosine of x, when it's at 0 at 2 pi, pi, and so on. Cosine is at positive 1 or negative 1. So that means that when cosine is at its maximum value, sine of x is increasing at its maximum value. So that's what we've written down right here. The derivative of sine of x is just equal to cosine of x. And here's all of them. We don't have time to go over every single trig function, but here's all of them. So sine of x is equal to cosine. Cosine is negative sine. Tangent is secant squared. That one's a little interesting. That one's important though, so I would remember that. Cosecant of x is equal to negative cosecant x, cotangent x. Once again, a little confusing. Secant x is equal to secant x times tangent x. And then cotangent is just negative cosecant squared x. So you can see the relationship between tangent and cotangent. Obviously, secant and cosecant also have a very similar relationship. Sine and cosine have a very similar relationship. So very cool. There's trig derivatives. I would memorize all of them. Technically, I don't think cosecant and cotangent are as important, but I would memorize them. All right, here's inverse trig functions. So this top graph shows just sine inverse of x, all the inverse functions when you're just taking them of x. So you have all of these weird fractions. I'm not going to talk about all of them. Secant and cosecant are a little less common because of this absolute value of x right there. It confuses things, so you don't see cosecant and secant as often, or the inverse of cosecant and secant, but they still exist. And then here's really important for integration. Both of these are, but this down here is really important for integration, I would say. It's when u is a function. So u is not just x, it's a function. And once again, I'm not going to go over all of them, but there they are. So once again, down here, this is when u is a function. Up here is when you're just, sine inverse of x. This is arcsine. So, I should mention that. Arcsine is the same as sine inverse. So when you see arc in front of a trig function, you just know that it's inversed. And then let's talk about exponential and logs. These are really cool. I like all of them. Here's the big boy. E to the power of x. The derivative of e to the power of x is e to the power of x, which is really cool to think about. The fact that e to the power of x grows as fast as e to the power of x. That's really interesting to think about. There's so many videos out there talking about how cool that is. I can't talk about how cool it is in its entirety, but I'm doing it a disjustice by saying how cool it is. You need to see how cool that is. The derivative of just a number to the power of x is equal to ax times the natural log of a. So yeah, this is where a is a number and it's not e. And then let's talk about the derivative of the natural log is just 1 over x. Once again, really important. These two are probably the most important derivatives I would memorize. They're all useful for integration. They're all very useful in general. Natural log is 1 over x. And then the derivative of a log with a base that is not e, so not the natural log, is equal to 1 divided by x times the natural log of a, so the natural log of the base. Alrighty, product and quotient rule. So now we're finally out of all of the of the derivative identities. Now we're going to talk about some rules. So here's the product and quotient rule. So where f and g are both differentiable functions, the product rule states that the derivative of two products is f prime of x times g of x plus f of x times g prime of x. So you have to take the derivative of both functions and multiply them by the original functions, if that makes sense. Here's the quotient rule. I almost said the division rule. The quotient rule. So once again, f and g are both differentiable functions. It's equal to g of x times f prime of x minus f of x times g prime of x divided by g of x squared. So this is a little saying that helps me remember. You can say low d high minus high d low all over low low. So the bottom function times the derivative of the top function minus the top function times the derivative of the low function, and it's all divided by the bottom function twice, so low low. And here's it written in a different way. But yeah, this is just the quotient rule. I wish I put the power rule as well. Power and quotient rule are easy. They're hard to get used to, and sometimes you might forget, but they're easy. You just got to remember that you take the derivative of both of them, and then you multiply by the other. The chain rule. So this is dealing with composite functions, so a function inside of a function. Think of sine of x squared, where x is to the power of 2. That's a composite function because there's two functions happening there. There's x squared, and then it's inside of sine of x. So a composite function has f of x and g of x. Both are differentiable, and it's written in the form f of g of x or g of f of x. And here's what the chain rule states. So the derivative of a composite function is equal to the derivative of the inside function times the derivative of the outside, keeping the inside of the function the same. So the only way that I think I can describe it easily is thinking of an Oreo, where the cream represents the inside function and then the cookie represents the outside function. There's lots of people out there, like I said right here, they're sycophants. I don't like that. But lots of people like to eat the cream first. So they take the cookie apart, they eat the cream, and then they eat the cookie. I think it's stupid. I don't know why people do that, but I've seen it happen more than once in my life, and I've seen it all over online. So yeah, if it helps you when you do the chain rule, think of a cookie. Think of an Oreo. Where the cream represents the inner function, cookie represents outside function. You eat the cream first, and then you eat the cookie. Okay, here's implicit differentiation. So if you remember way back at the beginning of the video, where I talked about d over dx and dy over dx. So when taking derivatives of functions, it's normally done with explicitly defined functions. So if a quick reminder is needed, that means when the equation is solved for a certain variable. So you'll have y equals x squared. The equation has been solved for y. If you think about the notation we've been using and dy over dx, this means that we are deriving an equation y with respect to the variable x. And once again, normally that's fine because you're deriving x with respect to x when it's explicitly defined. But what if it's not? This is really common. This is the equation of a circle. So it's x squared plus y squared equals r squared, where r is just a number. It's the radius. So while it's possible to make two equations that are solved for y and you can just derive them normally, you can actually just derive it anyways using implicit differentiation. So here's the big thing. I should have highlighted it. When you derive something that is not in respect to the variable you are deriving with, you must indicate that with d blank over dx, or whatever variable you're differentiating with. Sometimes it's t. So here's a practice problem. It says find the slope of a circle given by x squared plus y squared equals 25. So the radius is 5 at the point 3, negative 4. So first, if we're finding the slope of something, let's take the derivative of it. So once again, d over dx is an operator. Technically, you're supposed to write it on both sides, but I'm too lazy to. Let's take the derivative. So using our new power rule, we can just say that the derivative is 2x plus 2y. But there's an issue here. You took the derivative of y with respect to x. When you took the derivative over here at 2x, you're taking the derivative of x with respect to x. So there's no issue there. Technically, you can write dx divided by dx, but then the dx's will just cancel out because it's with respect to itself, if that makes sense. But over here, you're taking the derivative of another variable. So you have to indicate that this is the derivative of y with respect to x. And it equals 0 because 25 is a constant. The derivative of that is 0. And now that we have this equation, look at the green. Solve for the slope, dy over dx, because dy over dx is slope. So you subtract 2x and you divide by 2y to find that dy over dx is equal to negative x divided by y. And then let's take it further and plug in the point 3, 4. So the slope at that point is 3 over 4. So really easy. Implicit differentiation is easy, but the biggest thing to forget about it is just that you have to do it in the first place. It's really easy to look at an implicit function and just be like, oh, let's take the derivative really easily. And then you accidentally take a derivative of y when you're differentiating it with respect to x. So, like I said, the hardest part about implicit differentiation is remembering that you have to do it implicitly. But aside from that, it's really easy. This practice problem, shows how easy it is. Once you take the derivative correctly, you just have slope in there. This will come up again, by the way, in differential equations. It'll come back up. Okay, let's talk about our final thing for today, L'Hopital's rules for indeterminate limits. So as a reminder, an indeterminate limit is when a rational expression, so here's f of x and g of x, results in something that is impossible to solve. And I wrote it right here. So you have, normally it's 0 divided by 0 or something divided by 0, plus or minus infinity divided by plus or minus infinity. Those are really the cases where it's indeterminate. So L'Hopital's rule states that if you have the limit and it's indeterminate, where the limit as x approaches c of f of x and g of x, you can just take the derivative of the top and the bottom and compare the rates of change. So it says this limit is equal to this limit with the derivatives. And here's why L'Hopital's rule works. Because how I saw it explained that made sense to me is when both functions break, like you have 0 over 0 or infinities involved with it, that means that the function is broken. You can't, once again, infinity is a concept. You can't have infinity. Dividing by 0 is a concept. You can't divide by 0. So when it breaks, it's still helpful to know for a limit how fast that happens. And what better to tell you how fast something happens than its derivative. So you can compare the rates of change in a limit and still get the same answer as the original limit. I really wish I wrote it. That one limit we kept on coming back to last episode could be solved really easily with L'Hopital's. It was x squared minus 4 divided by x minus 2, and the limit was approaching 2. You could really easily solve that with L'Hopital's rule without even a second thought. But yeah, aside from that, that's basically everything you need to know functionality-wise of derivatives. The only thing I can think of that might come up is inverse derivatives, but I'm not taking time to go over that. So inverse derivatives is the only thing I didn't really go over in this episode. Aside from that, you should be, good on taking derivatives at this point. You know all of the rules. All of the identities with trig functions, inverse trig functions, exponentials and logs. The rules, and then implicit differentiation. Taking derivatives is actually really easy. I love doing it because at some point it just becomes second nature. You don't even have to think about it. Sometimes I'll be taking a test and I'll even be like, did I take that derivative? Oh yeah, it already happened like in 1 second. So taking derivatives is easy. And yeah, overall derivatives are really cool. Once again, my next video is going to be the functionality of derivatives. So you're going to go over things like optimization problems. You're going to go over related rates. We're going to be going over how derivatives relate to each other. We're going to be going over value theorems. All of that is all in the functionality of derivatives. So yeah, thank you for watching. I hope you learned something interesting about derivatives. And thank you.